The topic for today, or for this lecture, is the chain rule, section 15.4. Just a quick reminder, remember what it looked like when you were doing this in Calc 1, I guess. You had a function composed with another function, said something like f of g of x. And we're looking for the derivative of that. And, well, you know, it's a little bit complicated. It's the derivative of f, but still applied to whatever g of x was. And then afterwards you multiply by the derivative of the inner function, g of x. You get g prime of x on the backside. Classic example would be something like e to the x squared. We're taking the derivative of that. You first take the derivative of e to the x, which is e to the x. But I'm not going to write e to the x because this one had an x squared in it, and this one's going to have an x squared in it as well. And then the tail end part here, where we multiply by the derivative of that inner function, that gets us a factor of 2x. If you see this, if you wrote this this in terms of Leibniz notation, it would look different, and in fact, it would look easier. So let me set up the way this is supposed to look. X is the basic input variable, right? And we're feeding x into a function g of x, or g. Do you notice how we don't have a name for that? This is what's known as a hidden variable, because g then just gets fed right into f. And then the output is called f of g of x. In Leibniz notation, things kind of work more smoothly if, rather than referring to the functions, you refer to the variables. So let's call this this variable, the value that comes out of g of x, let's call that u. And then y would be the output from f. What the Leibniz notation says to do is find du dx, and similarly find dy du, and you want to create something out of those two things that tells you how y changes as the input x changes. Just multiply them. And actually it looks as if, it's not quite true, but it looks as if you just cancel the du's. So you get dy dx. Now, this is a slight lie, because really the functions are there, and when we calculate a derivative, we actually want to know where we're calculating it. And thinking about where these things get calculated is what lets us really understand this form. If we were trying to do this at some value for x, call it x equals a, okay? Then du dx, the derivative of, that's really the derivative of g, that would get evaluated at x equals a. But if we want that to correspond to this guy, where should this guy be evaluated? This is how f is, this is a derivative that tells us how the output y changes as we change u a little bit. But if we expect these to happen at the same place, this has to happen at u equals g of a. And where is the dy dx actually being calculated? That's when we sort of think about this as not being broken up into these chunks, but there's one function, happens to be a composite, but one thing which takes x as input, gives us y as output. So that one would be also evaluated at x equals a. That is, without the evaluations on here, it's really much simpler. It just says take the products of the two derivatives. That's what the composition's derivative is. So do you see why this f prime had a g of x in it and this g prime didn't? It's to make these things literally being evaluated at corresponding moments, the corresponding positions for the inputs. G is, well, look what G is getting as its input. It's getting X. So G prime gets X. But F is not getting fed directly. It's not having X directly fed into it. It's got G of X fed into it. That's why the thing looks a little more complicated. It's just that F prime needs to be evaluated at the place that corresponds to where G prime is evaluated. This guy happens at X, this one at G of X. The Leibniz notation just sort of sweeps that under the rug, which in some sense is a better idea, I think. All right, so that's a quick tour of Calc 1 chain rule, but we're now going to do Calc 3 chain rule, which is much more involved and yet is basically the same as what we just saw. So first off, let's think about compositions when we're in multivariable situations. The thing that we just looked at was a chain that's made by feeding one function's output into the input of another, right? That's the basic one variable composition. What if we have, in place of this box, we have something like this, where, say, a parameter t comes in and a vector with x and y components comes out? What can we hook that kind of thing up to? Well, here's an idea. We can hook that sort of thing up into a box that takes two inputs, x and y, and produces a single output. Maybe z. Now, physically, what have I just described? I mean, I was just thinking about how to hook together black box diagrams, but this is actually really interesting. A single input, a parameter, a vector as output. This thing here is a function like the position function in a vector, in a space curve. This is like R. And what is this guy? Well, that's two inputs and a single output. This is a surface. This is something like f of xy. What does it physically mean to compose a space curve with a surface? T tells you where you are in the xy plane. F tells you how high you are above the xy plane. And the two of these things put together is going directly from t to z. Given a time, it figures out an altitude. Well, that's one way you can hook functions together to get compositions that you might then worry about the derivatives of. But there's more. For instance, let me give you an example like this. Suppose I had two inputs, x and y, and a single output. So that you might think of this as x and y going to z. But then, well, for instance, one thing you could do from there is just have one more function. That's an ordinary Calc 1 style function. So this guy would be something like our f of x and y. This guy would be, what's another name for, how about g of z? Now I've done the drawing for it here. How do you actually write a formula for that? The inputs first go into f, and the output of that goes into g, which you would write this way, g of f of xy. One more place. Turns out there's actually lots and lots of ways to hook functions together to get compositions that well, are useful in certain circumstances. This is probably one of my favorites, but we can do things like this. You can even do, I should show you, we can do some really oddball compositions. Yeah, let's just give you this last oddball one up here. What if I had two inputs going into a function that had 3 outputs. And those 3 outputs were fed into another function that went maybe to a single final output. So that's a pretty complicated setup. But overall, if you think about the overall structure of this composition, it's 2 inputs and a single output. Well, that's this kind of guy, right? That's our z equals f of xy kind of machine. You know, x and y going in, z coming out. What about these other wires? I mean, you could say, oh, those are just details of the computation, so we don't care what they are. But, you know, often we would know what this function is. We would know what this function is. We'd like to be able to do things like take the derivative of this thing in an intelligent way. So it actually is useful to have names for the intermediate variables, or sometimes called the hidden variables. How about, let's go Greek, alpha, beta, and gamma. Those could be those values on those hidden lines. So given that we can have a lot of complexity in how we make compositions, it's interesting that the chain rule still works its magic in a reasonable and easy to understand way. What you do, well, actually there's 2 ways to approach this. So let me show you actually my favorite approach, and then I'll show you how they do it in the book. Let's look at the case where a space curve, that is t going to x and y, is being fed into a surface. So this is like r, and this is like f, and we're getting z as the output. T, x and y now are the hidden variables, because if you think about the composition overall, it's just taking you from time to height. All right, so I want to show you how to think about the derivative of this. And it is basically, the way you think about it is, how can t influence z? It can go one way through x to have some influence on the output of z, but it can also have an influence on y, and that has an influence on z. So you see there are 2 paths through this little diagram. Well, for each path, we're going to do the 1 variable chain rule. And then we'll just add them together. And it turns out that is the right thing to do to get the derivative. What would you call the derivative of this overall thing? It would be, you know, z is the output, t is the input, that's dz dt. And I just said, for each of these paths, what we're going to do is find a derivative in each chunk, and we'll multiply them. So I would have dx dt, which comes out of r, and then partial f, I'm not going to call it f, sorry. We should really stick with the variables when we're talking Leibniz notation. So partial z, partial x. That's just the top route, how t influences z through the line that goes through x. And you'll notice that x and x, there's sort of a cancellation that's going to happen. This is part of the derivative of z with respect to t. Well, the other part happens by following this lower line, which is going to be dy dt times z's y derivative. That's partial z, partial y. And what do you get when you take part of the derivative plus part of the derivative? You get the whole derivative. That's sort of the zen of this. Okay, so let me redo this one in the way that the textbook would do it. They think of r here as actually being, inside of it, it's got a pair of regular 1D functions. So a slightly different, oh darn, I've not planned my board space well. Well, let me do this. You think about t feeding into r there, but what really r is it consists of a function that gets the x coordinate and another function that gets the y coordinate. So the input branches here, goes to both of those, and that's how we get our two outputs. When we did this, I believe we called the components of R f, g, and h. So since we've only got two variables, let's just call them f and g. Now, unfortunately, I called that one f. Can we break that and just call it phi? That looks like an empty set sign. I mean phi, like the Greek letter for f. Just so we have a new thing there. Phi is something that has an x input and a y input and gives a z output. So it's a surface. That's the way we think of this setup in the book. And what they have you do is make a diagram that shows the dependency of variables on other variables. In particular, the hidden ones are important. So z depends on x and y, right? And x just depends on t. And y just depends on t. I kind of wish these two t's were the same, but this is actually how they draw the diagrams in the book. Well, each of these little line segments that shows a dependency, it comes about because of a function. The time dependency of x comes from this function f. So what's the, well, let's call it f prime. That's the derivative of function f. The way that z depends on x comes from this function phi, and the derivative of that, well, we would call that phi sub x. This dependence, where y depends on y depends on t, happens because of g. Then the line will be labeled with the derivative of that. The last line here is going to be labeled with phi sub y, because it's through phi that we get some dependence on y. Z gets some dependence on y because of the function phi. Phi sub y tells you how that dependency's derivative looks. So then your job to make the full derivative is to just multiply along these chains. I think maybe that's another reason why they sometimes call these things, call this thing the chain rule. So what would I have? F prime phi sub x plus g prime phi sub y. That's literally the same thing as this, just with different names. This one emphasizes what the functions are, this one emphasizes what the variables are. And a lot of times, by the way, we name the function with the name of the output variable. So sometimes these things look identical. It depends whether you made a separate naming convention for the functions as if they're different from the output variables, or I could have just called this one x of t and this one y of t. Then the output variables and the names of the functions would agree with one another. If that was the case, what would I be? If I was trying to do the same thing with phi here, I would call it z of xy. And again, you would see that there's really not that huge of a difference between the two notations. Although, boy, this looks a lot smaller and easier, doesn't it? Well, partly it's because I didn't say that. I never said what we were getting out of that. This is z's derivative with respect to time, so that's z prime. So I think it would be smart for us to do an actual example of this, because because we can. So I'm going to make this setup here where we have t feed into a function that gives us a vector's worth of outputs, an x and a y, and those guys go into another function. I'm thinking of them as r and f, and we get z as the output. So what I want to do in particular is r of t is motion around a circle, so cos t sine t. And f of x and y is just take the product of them. Now, well, yeah, let's just take derivatives of everything in sight. We know how to take derivatives of these things. I'll take the derivative of r and get r prime, which is cos becomes minus sine, sine becomes cos. And taking the derivative of f, well now wait, f is one of these things where we've got two inputs. We can't take just one derivative, there's two choices. We can take the x derivative of it, and we get y, because, wait, the x derivative is y? Seriously? That's weird. Yeah, it is, because y gets treated as a constant, and when you take the derivative with respect to x of x, the x turns into a 1, so it's just 1 times y. And then f sub y is x. Weird. This is the same logic though, right? When you're taking the y derivative, you treat x as a constant, so you get x times the derivative of y. The y derivative of y, so that's a 1. So x times 1, x. All right, so let me do this via my paths through the diagram bit. There's a way in which t influences z by passing through x. And the derivatives that are needed for that piece are the x-coordinate of r's derivative. That's what we're going to find here is dz dt. But I'm breaking it up into these two pieces. The derivative of the x-coordinate of r, which is minus sine t, times the x partial of f. Cool. Plus, there's going to be a piece where we pass through the lower branch of that thing, and there we need the derivative of the y-coordinate of r, which is cos t. And then the derivative of f here with respect to its y input variable. So that's, oops, just about right. I just was going to write f sub y, but we know what it is. It's x. All right. So far, so good, except, wait, there's a problem here, isn't there? This one has got t, and that one's y. This is t, and that one's x. I got to be able to write all this stuff in terms of the same thing, don't I? Well, what are y and x? They're the outputs from r here, right? So x is that position, and y is that position. In other words, you can replace y with sine t. And so we get minus sine squared t. And you can replace x with cos t. So we get plus cos squared t. All right. That's an answer. And it came from the chain rule. Fortunately for us right now, there is indeed a way to test or to check our answer. And so let's go through that. Remember we got minus sine squared plus cos squared. In fact, I'll just leave that on the board so we'll erase around it, but we'll leave that there so that we can verify eventually. Whoops. Didn't want to erase the input. Right, so can we figure out an expression for z straight up in terms of t? In other words, can we just deduce what the composition looks like? Yes, we can. T produces cos x here and cos t here and sine t here, and then F just multiplies those things. So you could think of the composition as being Z is the product of cos t and sine t. Yeah? Well, we've been through this ringer before. Can we take the derivative of a product? Of course we can. So here we get dz dt as the product rule. So the first times the derivative of the second. Well, that's cos squared t, isn't it? Plus the derivative of the first. Okay, so it's minus sine t times the second, left alone. Just came up in a different order. What's kind of fun at this point is to show you how to get the product rule from this very setup. Yeah, in fact, let's take a second and do that. Suppose I've got two functions that both take t as the input. T goes into f, and so f of t comes out, and t goes into g, so g of t comes out. And then I plug these outputs from f and g into the multiplier function. Well, let's call it m. It takes the product of the two things. Right? So if we called this one x and this one y, and we wanted to describe multiplication in terms of them, we'd say x times y. Well, that's something we can do the multivariable product rule with. There are two paths through this diagram, from starting at t and ending at the product of x and y, or z if you like, and this one through the top, starting there. So what are the derivatives of things along those paths? Well, the first one is f prime at t times the multiplication function's x derivative, which we saw previously was y. And then the other path through the thing, the bottom branch, the derivative of g is just g prime. But the derivative of this multiplication function with respect to its second input is x, is its first input. Yeah? So this is, if we call this guy z, what we've got here is an expression for dz dt. But we have the same problem we had last time. There's a mismatch. Some of the things involve t, others involve x and y. Can we sort that out? Yes, we can, because y is g of t. So this is f prime of t times g of t. And this other one, g prime of t, okay, I'll just write that, times x, which is f of t. Recognize the product rule now? I know it's got them in the wrong order, and some places are f and some places are g. You only have to be really careful about the order in the product rule if you're going to then go on and talk about the quotient rule, because there it matters. But when you're multiplying and adding it, who cares what order it's all in? It commutes. So that's kind of cool. This multivariable chain rule kind of drops the product rule out for us without any muss or fuss. I don't know if some people will go through the proof of the product rule in Calc 1, and what you have to do is refer back to the limit definition of these derivatives and do some very finicky manipulation with derivatives, or excuse me, with limits. But here it falls in our lap. We don't have to do anything difficult. I want to show you another place where the multivariable chain rule actually makes something that formerly seemed complicated kind of very obvious. And this is a topic, again, back to Calc 1, implicit differentiation. Remember that? I think that was a difficult thing for a lot of people to get their head around. Whoops. Implicit differentiation. This is used when you don't have an explicit formula. So you don't have that y equals f of x. Sorry, we don't have that. What instead we're going to have is a relationship between x and y where neither one is better seen as the output and the other as the input. So things like, well, this is a simple and very useful one. Now, admittedly, you can take this relationship and solve it for y, and you get, let's see, y is the square root of 1 minus x squared. And that's actually wrong because it's plus or minus. See, it's better to literally stick with the implicit version of things and use implicit differentiation here. Remember how that works? I'll just refresh your memories. You pretend y was a function of x. You know it's not really, because this is a circle, yeah? And vertical line tests are dying all over the place on that. So it's not a function, but you pretend it is. So you write x squared plus y of x squared equals 1. And now you differentiate, and you get, well, you get 2x. I'm differentiating with respect to x, right? So I differentiate x squared, and I get 2x. And then I don't know what y's derivative is, but I'm going to write it as y prime. What am I thinking? Don't want to write that first. I want to take a look at the outer function first. We're squaring y, right? So we want the double of that. And then you have to take the derivative of the inner thing, y prime of x. That's where we want the y prime to be. And then on the right-hand side, you get 0, because it's a 1 over there. Yeah. Now you stop pretending that anything's a function of the other thing. You just call that y and that y prime, and you solve for y prime. So you write this as 2x plus 2y times y prime equals 0. Y prime, that is. So can you solve it for y prime? Yeah, it's not bad. You subtract 2x and then you divide by 2y. So you get y prime is negative 2x over 2y. And actually you can simplify it one more notch. It's negative x over y. Which I'll point out is interesting because that's a formula for the derivative of y, for the slope of a tangent line on that curve, that you can do anywhere at all in the plane, right? You can put any x and y. Well, I guess you can't put y equals 0 in there. Yeah, what would y equals 0 correspond to? It would be these 2 points on the circle where the tangent line is vertical, right? But you could also have y equals 0 here, and apparently we'd have a vertical tangent line here. We could have a point way far away from the circle and get a slope for the tangent line. When we put this in the guise of thinking about multivariable chain rule, that begins to make sense. So let's do that. So when there's an implicit connection between two variables, you can always move everything to one side and set 0 on the right-hand side. And we want to think of this relation now, this relationship between x and y, in the following sense. We want to be able to write there's some function of x and y that's equal to 0. Really, this would be whatever the relationship was between x and y was, but we'll think of that as a function. and now it's in the multivariable setting. It's got two inputs, right? There would be variables x and variable y's in there, and if it wasn't equal to 0 on that side, that's fine too. You can just leave a constant over there, but you don't want to have anything variable on the right-hand side, because what we're going to do is take the derivative of this. All right, so let's try that. Well, first, we are going to play the same game that we played when we were doing this in Calc 1. We pretend y is a function of x. So that is, we don't just straight up differentiate. We think about f of x comma y of x equals 0. And we want to differentiate that. Pictorially, what this would look like is you've got an input x, which goes into f, but it also goes into a function that produces y. And then x and y both feed in and come out. Well, actually they come out to come and give us a 0. This big guy is our capital F. And this little guy, I'm going to name it y because that's how I wrote it right there. Its name corresponds with its output variable. Still, when we play that same thing, how does x feed into f? Sorry, how does x feed into this output and produce some effect on the output? It might be, actually it would be nice to think about this sort of symmetrically. So what function should I stick in there so that it just looks the same, but this is still an x on here. This is not changing x. People call that the identity function. F of x equals x. All right, so we've got the identity function, and then we've got the function that produces y as the output on a given input x. Let's think about how the derivative looks. The derivative of the identity function, that is the derivative of x with respect to x, times f's x partial. Let me write it in the Leibniz notation just to get you used to that equally. I don't want to use one notation strictly. It's better to get facile with using both, switching between them. And then the other branch through the function, through this diagram, gives us, what is that? Function's got its y is the output, x is the input. That's the derivative of that is dy dx. And the other piece of this, the product, as we remember we do a product as we trace through one of these branches, is f's derivative with respect to its second input. That's partial f, partial y. And on the right, of course, you have 0. Now, what is, that may look weird, but it's really not. What's the derivative of x with respect to itself? If I wrote it this way, d by dx of x, you might get it. That's like saying x prime. That's 1. So we've got some partial derivatives around, but this is kind of cool. We can solve for dy dx out of this. And notice I was doing this quite generally. I didn't say anything about, particular functions. It's like we're doing all of the implicit derivatives from Calc 1 all at once. Crazy. Yeah, so let's solve it for dy dx. You're going to move that partial f partial x to the other side. It'll be negative, and then you'll divide by this guy. So it'll be dy dx is equal to partial f partial x, negative partial f partial x, because it's on the wrong side of the equation right now, divided by partial f partial y. Or an alternative and more compact way to write that, it's the negative of f's x derivative over f's y derivative, y partial, I should say. So let's put that one to use. A famous family of implicitly defined curves would be this guy. Y squared equals x cubed minus 1. I don't know how well this is going to work out, but I want to try it on my cell phone. I've got the Desmos app on here. And I just fell in the Duolingo stats, and it just told me that I need to go practice language. So shortly I will be finishing this and doing that. Here's Desmos. You see it okay? There it goes. Let's put that in. Y squared equals x to the third power minus 1. I can't tell now whether you're seeing that okay. Now you can tell that's not a function, right? Because the vertical line test is failing on it. It's an implicitly defined curve, but we can work out the slopes on that curve very easily now. How do we proceed? We write a function that basically encapsulates putting everything to one side in this equation. So I would write it as x cubed minus 1 minus y squared. Okay? I will take the pieces I'm going to need are its x partial derivative. So f sub x, it's really just 3x squared and then 0 and 0, so 3x squared. F sub y is 0 minus 0 minus 2y. And then dy dx on this implicitly defined curve is going to be 3x squared over 2y. The minus sign from the formula and the minus sign from that just knock each other out. So 3/2 x squared over y. Didn't seem like very much work, whereas implicit differentiation used to be hard. It's just kind of fun. The multivariable chain rule fixed it up for us. There's one last thing I should probably do. Kind of hate to do this because it's mind-bogglingly ugly, but it still is part of the multivariable chain rule, and it lets us see some of the real power of that. There's a kind of function that looks like a spider. It has multiple inputs and multiple outputs. One example of this kind of thing is changing coordinates. Imagine, you should have seen spherical coordinates before. That would take like x, y, and z and return rho, theta, and phi. That's a change of coordinate. And this function, actually what we do inside of here is we figure out a separate function for rho, and a separate one for theta, and a separate one for phi. We also have an inverse function that goes from spherical to x, y, z. But that's just an example. We've got many different functions that have this kind of overall shape of multiple inputs, multiple outputs. Let's not go too crazy and make a three-dimensional one. I want to see what happens if I have a two-dimensional function of this sort. That is 2 inputs and 2 outputs. And then let's feed those into a third function of the surface kind, right? 2 inputs go to a single output. I'm going to call the parameters back here s and t, the hidden ones x and y, and the output z. I need a name for this function. How about, well, actually, let's be a bit more honest with ourselves. This guy inside of it has a function that I would call x, which is a function of s and t. So in here, in the inner workings of this function, there's something called x of s and t. And similarly, that has both of these guys feeding into it. Similarly, in the interior of that function, there's y of s and t. And that's got plumbing too. That's got to have s and t both feed into it. This one we can just call f, I suppose. All right, now this is where things get a tad hairier. If I try to draw for you all the ways that the input variables can influence the output, you see there's some complexity. S could feed through x and then through into z, or s could go through y and then on into z. T could also go through x and then to z, or through y and on to z. So there's this is a place I think where the book's version of the diagram, maybe it's better. Z is your output variable, and it depends on x and y. And each of those depend on s and t. So the products that we need to do are through these branches. X's dependence on s, and z's dependence on x. Well, let's go ahead and write it down. Notice that these guys all have, we're in the partial derivative setting because x has two inputs, y has two inputs, z has two inputs. So what would it be? It would be z's x derivative times x's s derivative plus z's x derivative times x's t derivative plus z's y derivative times y's s derivative plus finally z's y derivative times y's t derivative. That whole mess? Wow, that's wrong. That's wrong, actually. I don't know why I wrote that. Why did I write that? I should have known ahead of time what I was looking for. See, if you think about this composition overall, could have put it all inside a black box, what sort of thing do we have? It's a single output that depends on two inputs. I don't have a derivative. What I just wrote down would be a sum of partial derivatives. Presumably it would be a derivatives, but that's not the right thing to do. What I want is a partial derivative of z with respect to s, and a partial derivative of z with respect to t. So this, totally not what I should have done, but instead, let's figure out what z's s dependency is. That's better. Let me draw them in a different color. There's two routes through this which hook z to s. One goes like that, and the other like that. So some of the terms that I named over here go into the s partial of z. It's z's x derivative times x's s derivative. That one. But we also have z's y derivative times y's s derivative. This one. The remaining two things, I've got them crossed out multiple times now, but the remaining two things tell you how z depends on t in the end, z to t. So we have z's t partial is z's x partial times x's t partial plus z's y partial times y's t partial. Excuse me. I think we'll need to do a quick example of that, and then we'll be done for today. So this would be for next Monday. Yeah, I won't need to So I'm going to go through, this is example 2 in the book, in section 15.4, where z is equal to the sine of 2x times the cosine of 3y. You see how z is a function of x and y? Great. Now, but there's more. X and y have dependence on s and t. So this is fairly simple. It gives x is the sum of s and t, and y is their difference. Make sure I do the same order, s minus t. Okay, so can we find all the elements that we're going to need to do this? Yeah, I think so. I'm going to want z's x partial, which is take the derivative of this with respect to x, meaning y here is a constant. If y is fixed, then the cosine of 3 times y is fixed. So that's just a constant times the sine of 2x. So you get the cosine of 2x times 2 times that constant, cos of 3y. That's z sub x. Z sub y is pretty similar, except now we're going to think of x as being the one that's fixed. So this is just a constant multiple of the trig function, cos of 3y. So we get sine of 2x times cosine's derivative is minus sine. All right, I want to put the minus out front. Minus sine of 3y, and ordinary chain rule means we need another 3 there. Okay, that's z sub x and z sub y. We're going to need x sub s, x sub t, y sub s, and y sub t also. Those are quick. X sub s is 1, right? Because the derivative of the variable plus a constant, the constant goes away, the derivative of the variable is 1. X sub t is also 1. Y sub s, that's 1. A lot of 1s. But y sub t is negative 1. So we just need to use these 6 things, the partials of x with respect to x of z, and partials with respect to y of z, and all these partials of x, y with respect to s and t, into the formula. Let's remind ourselves how the formula is going to work. You have this is the table, or the diagram that goes with it. X and y depend separately on s and t, and then they each influence z. Well, I should be able to write this just at the very bottom of the screen. If I'm looking for the partial of z with respect to s, that will involve, let's do colors again, that will involve these branches that go from z down to an s. Right? So we'll multiply along those branches and then add the results up. That is z's x partial for the little bit here times x's s partial, which is just a 1. Okay, so we just copy that in. Cos of 2x times, actually I want to put that 2 in the front. 2 times cos of 2x times cos of 3y. That's the branch that corresponds to x and s. But we also need the y and s branch, which would have y's s derivative is 1. Don't have to worry about that. Z's y derivative is this expression. Okay, so it's minus. I'm going to put the 3 here into the front again, just like I did. I like my constants to go up front. Just that's a thing with me. Sine 2x sine 3y. Huh. The z sub t is similar, so I think I'm gonna give myself a break and not do that, but there is something more that has to happen here right now. And it's a question about almost about politeness. Z's partial with respect to s should be a function that talks about s. I suppose it might have t's in it as well, but it should certainly have s in it. And x and y that are in here, these are these hidden variables that we really don't care about. You're supposed to be thinking about getting something that tells you how z varies as s changes. It seems weird to mention x and y, but fortunately we can get rid of them with these relationships. X is s plus t, and y is s minus t. So I'm going to squeeze this in here. This is equal to 2 times the cosine of 2 times x plus y. Oh, I'm sorry, s plus t. Wow, forgot the word cos there too. 2 times the cosine of 2s plus t times the cosine of 3 times s minus t minus, I am going to run out of board, and I'm here on my knees doing this thing. It seems pretty silly, doesn't it? Yeah, all right. I'm like really tempted to quit, but definitely I'm going to quit being on my knees. I'm going to take this minus and we'll put the rest of this up at the top of the board. Where were we? We had cos of 2x, cos of 3y, then we're subtracting 3 times the sine of 2x. Just replace the x with s plus t. Times the sine of 3y, and y is s minus t. I should stop being a wimp. Let's do the z sub t too while we're at it. Since we've now got room to work, z sub t was, it'll be z sub x times x sub t, which is 1. I'm just going to write it first, plus z sub y times y sub t. I think it's probably worthwhile pointing out to you that there's always a matchup in these things that looks like that, a little x and a big X, a little y and a big Y. And both of the things had better be the t's here, that you're getting part of the information about the partial derivative from each of those terms. But it's a little bit like in the Leibniz notation where the x's and where a dx cancels with a dx. Yeah, all right, so what is this going to be? X sub t is 1, y sub t is minus 1. So what we're going to have is z sub x minus z sub y. And here they are. And I'm just going to, on the fly, put in s plus t's there and s minus t's there. Okay, so we'll have cosine of 2 s plus t. Oops, there's a 2 up. That should have gone out front. Times the cosine of 3y, which is s minus t. And wait a second, we had a negative sign and a negative sign that cancel each other, so plus sine of 2 times s plus t times, there's a 3 out here that I really wanted to not forget about, put it up front. That's the sine of 2, and then we need the sine of 3y times the sine of 3 s minus t. Did it. So there's Z sub t, and unfortunately Z sub s is split across from the bottom up to the top there. Phew. All right. I'll see you later.